Good evening, Low Six. I hope you enjoyed a bit of a break while you did your university preparation week from physics. But we've now got to come back and carry on with the electric circuits part of the syllabus. So at the end of the last bit of work we did, we had a look at voltage, current, and resistance. And then we talked about voltage current properties of different components, such as resistors, light bulbs, and diodes. What we're going to look at today is something which you may have covered at GCSE slightly. It depends on the syllabus that you did for GCSE. But we'll assume that you haven't met this idea before. We're going to look at resistivity of a wire. Okay, so if that's a new term to you, if you haven't heard the term resistivity, don't get it mixed up with resistance. We'll assume that you don't know anything about it, and we'll teach you it from first principles. Okay, so what is this all about? Well, if we go back to what we did in the previous week, we mentioned Ohm's Law. And Ohm's Law says if you've got a metal conductor, such as a wire, its resistance is constant as long as its temperature stays constant. So what determines the resistance of a wire? Okay, what I've got here is strung across my dining room table is a copper wire. Okay, and what determines the resistance of that copper wire? If I wanted to measure the resistance between these two crocodile clips, what would determine that resistance? Well, if you think about this logically, there are three things that determine the resistance of a wire, or indeed any physical shape of metal conductor. It doesn't have to be a wire, it could be a cylinder, it could be a long cuboid, it doesn't really matter, but wires are probably the most common use of this idea. So what are the three things that determine what the resistance of this copper wire is? Okay, well, number one, the length of the wire. Now this should be fairly obvious, because if I double the length of this wire, okay, now I've sectioned off a 30 centimetre length of copper wire here. If I was to double that to 60 centimetres, that would be like having two equivalent resistors, one after another, in series with each other. The resistance would add up, so it would end up having twice the resistance. So the resistance of a wire must be directly proportional to the length of the wire. That should be fairly obvious. You double the length, you double the resistance. If 10 centimetres was 1 ohm, 20 centimetres would be 2 ohms, and so on. Okay, so that's one property of a wire which determines the resistance. What about the width of the wire, the thickness of the wire? Now, rather than talking about the thickness or width of the wire, let's talk about the cross-section area of the wire. So if I cut across this wire, it would have a circular cross-section. I could measure what its area was. How does that affect the resistance? Well, if I doubled the cross-sectional area of the wire, it's almost like having a second wire in parallel, okay? So if I've got a 30 centimetre stretch of wire here, if I doubled the thickness of that 30 centimetre stretch of wire, it's almost like having two 30 centimetre stretches of wire between these 2 points. I'm doubling the wire, which also means I'm giving the current twice as many routes that it can travel across the potential difference between here and here. Okay, so I'm making it twice as easy for the current to flow. I can get double the current for a given potential difference. Now, if you get double the current for a given potential difference, another way of saying that is that the resistance has halved. So if you double the cross-section area of the wire, you half the resistance. Now, we all know what that relationship is. That's an inversely proportional relationship. So we've got two things so far. We've got the resistance of a wire is directly proportional to its length, and you've got the resistance of a wire is inversely proportional to its cross-section area. Okay, so what else have we got then? Well, the only other property of the wire that could affect the resistance is actually what the wire itself is made of. Now, this is copper. To be honest, the copper's not the best material to do this experiment with because it has a very low resistance. However, it was the only bit of wire I could find in the house, so I'm having to deal with it. So the actual material of the wire itself will determine what the resistance is, as well as the length and the cross-section area. Copper has a very low resistance for a given length or a given cross-section area. Other metals will have a higher resistance, and then you move into semiconductors, which have a much higher resistance, and then insulators, which have a vastly higher resistance for a given length and a given cross-section area. Now, the number that we use to define the material is called the resistivity. And where that comes in, I'll write it down for you because it's in the formula, and this is a formula that you do need to have to learn, okay? If you want to work out the resistance of a piece of wire, it's directly proportional to the length of the wire. It's inversely proportional to the area of the wire. And then the constant of proportionality, which has the Greek letter rho, that's this letter here, it's kind of like a curly P, okay? That is the resistivity of the material. And it's a constant for a particular material. So it's a constant for copper. You can go to a reference book, or you can go to Wikipedia if you like, as long as you cite the references in Wikipedia, and you can find out what the resistivity is of copper. Okay, it's a constant for a given material. So basically, this formula here, which you'll have to use, it's on the formula sheet, but you'll have to use it and learn what it means. The resistance of a wire equals this constant that depends on the material, called the resistivity, times the length in meters, divided by the area in meters squared. Area in meters squared can sometimes be problematic. You're often given a wire and you're told it's got a certain diameter in millimeters. Well, you'd have to convert that into meters, and then you'd have to halve it to get the radius, and then you'd have to do pi r squared to get the cross-section area in meters squared, which for a typical wire is a pretty small number of meters squared. It's something like 10 to the minus 7 meters squared. Okay, the unit for resistivity, well, we can think about this. That's ohms for resistance. That's meters squared for area. That's meters for length. So the unit, the standard unit for resistivity will be ohms times meters squared divided by meters. So it's ohms meters. So the unit is ohms meters. Okay, people sometimes get a little bit confused with this and put ohms per meter. Okay, it's not ohms per meter, it's ohms meters. It's ohms meters squared divided by meters. Okay, so that is what we mean by the resistivity of a material. It's a number that defines how good a material is at conducting electricity. It basically depends on the atomic structure of the material and the availability of delocalized electrons in the material. Okay, so obviously copper has a lot of delocalized electrons. It's a very good conductor, and therefore it has a very low resistivity. Okay, so I've explained what resistivity is. Why have I set up this this circuit here? Okay, now this is a part of well, it's a demonstration of a required practical that you will have to do. Obviously, we can't do it now, but we will be doing it when you get back in September, hopefully. You will do a required practical, which is basically investigating the resistivity of a wire. And the standard sort of setup for doing an experiment with resistivity is this. Now, back in the lab, we've got some nice sort of manufactured wooden boards with sort of wires placed on them. I haven't done that here. I haven't got that here, so I've had to sort of do a bit of a makeshift one by tying this copper wire to some chairs on either side of my dining table. But it works in the same way. What we've got is well, let me just move the camera a little bit out so you can see the whole lot. We've got a power pack. connected to a switch, an ammeter, and then the wire. If I just put this back again, there we go. So the power pack is running current through this ammeter and through this wire. There's also a switch, so I can switch the current off, which is quite useful because I don't really want the wire to get hot, because if it gets hot, actually its resistivity is no longer a constant if it gets hot. It doesn't obey Ohm's law anymore. So that's the basic setup. So I'm measuring the current going through the wire, and I'm also measuring the voltage across a particular length of wire. Now I can change this length of wire by changing the position of these crocodile clips. So at the moment I'm measuring the voltage, the potential difference across 30 centimeters, but I could just move this easily here. And now I'm measuring it across 20 centimeters. Okay, I could use the ruler to do that. Obviously, I'm not doing this particularly accurately here. I'm just sort of showing you this as a bit of a demonstration. So what is the whole point of this? Well, what we can do is we can measure the voltage across this part of the wire here. We know what the current going through is because we can measure that on the ammeter. If we do voltage divided by current, what do we get? Well, R equals V divided by I, so we get the resistance of this bit of wire. Okay. Now, let's supposing that we do that. Now, we might want to do a couple of repeats. So I could do 20 centimeters here, then I can move the crocodile clips along and do 20 centimeters somewhere else. Okay. What we'll get is the resistance of 20 centimeters. I can then increase the length and get the resistance of 30 centimeters. Increase the length again, get the resistance of 40 centimeters. So what we'll end up with at the end of the experiment is a table with the resistance against the length. Okay, so you'll have the length in meters and the resistance in ohms. Okay, obviously at the moment it's 0.2 meters length. Okay, let's just demonstrate this. So what we do, I'm going to switch on the switch, and then I'll show you how you'd measure the resistance. So I'm going to switch on the switch, and you can see we've got 1.42 amps, 0.17 volts. So if I then go and get my calculator, which is over here somewhere. Okay, if I get my calculator and I can do 0.17 divided by 1.39. So 0.12 ohms. So let me write this down here. 0.12 ohms. Now, as I said, you do a couple of repeats of this and take an average. As I said, copper has quite a low resistance, so it's probably not the best material to use. Something like Constantan or nichrome, which has a higher resistivity, would be better. So that's 0.2 meters. Now I'm going to increase this to 0.4 meters. Now again, if I was doing this properly, I'd probably turn the switch off to let the wire cool down, but I'm just doing this a bit roughly. Okay, so now it's on 0.4 centimeters, and you can see instantly that the current hasn't changed much. It shouldn't really change much at all because this voltmeter is perfect, but it's obviously letting a little bit of current through, which it shouldn't do. But 1.46 amps hasn't really changed, but we've now got 0.36 volts. So if I do 0.36 volts divided by 1.46 amps. Okay, and you can see there I've now got 0.25. So let me just turn that off. Okay, so you can actually see what's happened there. I'm not going to continue because it's fairly clear, but I've doubled the length and the resistance has pretty much doubled. 0.12 to 0.25 is very close to have doubled. So what you'll end up with is a load of measurements of length against resistance. You can then plot a graph with resistance on the y-axis, it's obviously measured in ohms, and then length in meters on the x-axis, and you should get a directly proportional relationship on that graph. You should get a straight line, okay, because as we explained before, resistance is proportional to length. Now, if I want to measure the resistivity of copper, what I would have to do is measure the gradient of that graph. So I'd measure the gradient of that graph. So I'd do delta y, make a triangle, a big triangle, and get delta y, delta x. I'll do delta y divided by delta x. Now, because R equals rho over area, that's resistivity over area, times length, this is a constant, isn't it? So R equals a constant times length, and that constant would be the gradient of the line. So the gradient equals the resistivity divided by the area. So the resistivity would be the area times the gradient of the graph. And voila, I've got my resistivity of copper, okay, which, as I said, is a very low number. Okay, I can't remember it offhand, but it's something times 10 to the minus 8 ohm meters. Okay, it's a really, really small number. The only thing there I would say is we'd have to measure the area. Okay, how would you measure the area of the wire? If you're doing this as a practical, well, you'd have to use a micrometer screw gauge, and you would measure the diameter of the wire in several places to take an average. You get the average diameter to 100th of a millimeter, because that's how accurate a micrometer screw gauge is. You then halve it, which will give you the radius. Make sure it's in meters, and then you do pi r squared, and then it would be in meters squared. Okay, and then you can basically just put it into this formula here. So the resistivity would be the area multiplied by the gradient. Okay, that's basically it. Okay, that's resistivity explained, and the resistivity practical explained as well. Okay, as I said, we can't do the resistivity practical till we get back in September. Bear in mind that you will have to do something very similar to this when we come back. However, there are some problem sheets on resistivity in the physics booklet, and so I will set you some homework to do for this week. So that's going to be a worksheet. I've also write some notes down for you guys to write down on resistivity. It's not a particularly lot of work this week, but it should give you an hour or two of work. And we'll meet on Thursday for a Zoom lesson. So I'll put a link to the Zoom lesson as well onto show my homework for you. Okay, that's it. Hope you have a good week, and do get in touch if you've got any problems or any questions. Thank you very much.